Experimental mathematicians, Doron, Zeilberger, who will speak about the experimental mathematics of voting. Thank you so much for coming. I really appreciate you coming. But maybe some of you are not familiar with the axioms. We're going to talk about axioms of voting very soon. But the axioms of this seminar, absolutely no texting, absolutely no grading, absolutely no emailing and everything else. Of course, you're welcome to leave anytime you want to text if you're not in this platform. I hate politics, but I love the mathematics of politics. I don't understand how people argue so heatedly about politics. Whenever people start talking about politics, I tune out. In my humble opinion, both of them are wrong, and all the issues are all trivial compared to all the other great, obvious injustices made today by humanity. For example, eating meat, it's much worse than all the bad things that you can have. So it's all excellent. But the mathematics of voting is very interesting. As you know, the current voting system in the US is dysfunctional, and everybody knows it. But most people, it's impossible to change because we have traditions and politics is stable. There are some reforms, there is some genius called Warren D. Smith who has a campaign for quite a few years about so-called range voting, in which you don't just vote for one person. You vote, you rank them, 10, 9, so Hillary 10, Jill Stein 8, Donald Trump minus infinity, so you can rank them, and then he claims, and he did simulations, that you get much more equitable and more reasonable outcomes. And the system in the United States is a two-party system because of this. That's why the Green Party or the Libertarian parties get many less votes than they should, because people do what's called strategic voting. They neither like Hillary, they don't like Trump, but as much as they hate Hillary, they hate Trump even more, and they rather have Gary or Jill or any of the other, but they don't want to quote-unquote waste the vote. So first is a plea, don't to do strategic voting. Strategic voting is immoral. You should vote to whom you believe in. And voting strategically to somebody that you don't think, you don't fully agree with is even worse than having Donald Trump as president. And my wife always tells me, oh no, I'm going to move to Canada, New Zealand, in Donald Trump. Yes, maybe it's bad, but voting against your conscience that strategically is unethical or even immoral. So that's my first plea. And in Israel, where I grew up, there is another system, a multi-party. You have lots and lots of parties. And these have advantages and disadvantages. The disadvantage is that nobody gets a full majority. You have to form coalitions. So often the two major parties, each of them get 40% and 45%. So to get a majority, you need the religious minority, 6%, and then rule everybody. That's why there are no buses in Israel in the Saturday, and you have to get married with a rabbi or a minister or a Muslim Qadi, but you cannot have civil marriages, and you have lots of theocracy. That's because of this thing. So there's no perfect voting system. So my former colleague who wrote my interview, Tzvi Arnstein, a very smart control theorist, had a revolutionary proposal, a little bit like range voting. Fractional voting. Suppose you are undecided. Oh, thank you for coming. Thank you for coming. I really appreciate you coming. But you didn't hear the axioms of this talk. Absolutely no using like devices.
Yeah, I just want to turn off the music.
Oh, okay, that's no problem. Thank you. So next time do it before you come. But thank you, man. I appreciate you coming. So it's a fractional voting. So suppose you have party A. So in Israel, it's the Likud, the Netanyahu party that I dislike, and then you have the Labour Party that allegedly is left wing, but it's really center right, and then you have lots of other parties. Suppose you are undecided, then you can just give a fraction. So Labour give 1/2, and then 1/4, and then some other. So have a fraction of your vote. Fit your vote instead of having a unit vector 1, 0, 0, or 0, 1, 0, 0, or 0, 0, 1, 0. Have a fractional vote. Unfortunately, this is not possible for the current system, but you can easily stimulate it. Thus, simulate in a computer, either do a random number generator and load the die. And then use a random thing, and whenever it falls, load the die, vote for this body. And Zvi Artline suggested it in Israeli TV, because in Israel is a rule, 24 hours before the election, you cannot have politicians talking and campaigning. So they're desperate, so they're so desperate, they can't politicians, they get professors to talk. So he gave this suggestion, and the guy shot an angry email. How dare you make me vote for a party I dislike? He didn't understand that you can easily have 0 for the parties you dislike, right? The people didn't get it, so he got lots of angry emails for this suggestion. But then I'm not going to talk about it. I'm going to talk about the great mathematics that was motivated by politics. So the earliest paradox, so to speak, is the Condorcet paradox. And today, the historic talk, I'm going to announce a brand new constant that modestly I would call the Condorcet constant. But hopefully, one of my students will write a paper and follow up and call it the Condorcet Zeilberger constant. Condorcet would never have come up with it all by himself. All he did was point out the following. If you have two candidates, it's not a problem. If you only have candidates A and B, you count how many people prefer A to B, how many people prefer B to A. Of course, if it's exactly the same, then you have to toss a coin. So if you have an even number of voters, it's not an issue. So let's stick to an even number of voters. Suppose we have 3 voters and 3 candidates, A, B, and C. Voter 1 has the following ranking. He or she prefer A to B, B to C, and of course A to C. It has to be transitive. We assume that every voter has a clear-cut transitive ranking. And the second voter, that's voter 1, has the following preference. He likes B best, C second best, and A the last. And the third voter, so in these 3 voters, an odd number, that's important, prefers C. Now see the contest, like in tennis, you have a round robin tournament, every pair. So A versus B, that's it, the outcome. 1 prefers A to B, and 3 prefers A to B. 2 people like A better than B. But, and 1 voter likes B better than A, 2 to 1. So A versus B, A won. B versus C, BC, voter 1 and voter 2 like B better than C. Only 1 voter likes C better than B. So, B won. Now A versus C, voter 1 likes A better than C, but he's outvoted. Voter 2 likes C better than A, and voter 3 likes C better than A. So you have a cycle. A beats B, B beats C, and C beats A. It's a cycle. It's a so there's no clear ranking in this case. So this is a minimal Condorcet scenario. So it's not that surprising. Lots of things in life are not transitive that you think. Being afraid of, intuitively, it should be a transitive relation. If A is afraid of B and B is afraid of C, A should be afraid of C. If A is afraid of B, if B is afraid of A, means A can beat up B. So it's stronger, it's bigger. If C is afraid of B, that means B can beat up C, is stronger. So obviously, if A is stronger than B and B is stronger than C, then A is stronger than C. Haha, I had a lot of examples in which it's not transitive. For example, here's one. Is the dog The dog is afraid of me. The cat is afraid of the dog. The mouse is afraid of the cat. My wife is afraid of the mouse, and I'm afraid of my wife. So it's a cycle. So it's not so surprising that Condorcet came up. So a natural combinatorial problem is how rare is this situation? So you don't only have 3 voters, you have n voters. For the sake of simplicity, to avoid ties, we have n odd. So you have alpha 1 to 3 voters who prefer 1 to 3. So you have a vector. So the outcome of the elections, you count how many people like, instead of ABC, let's do 1 to 3. Okay. ABC. So alpha ABC, the number of voters who like ABC better. A and then B and then C. So for every of the 6 permutations of 3 candidates, BAC, CAB, CAB, and CBA in anticipated order. So the outcome of the election, you have n voters, and each of them chooses one of these. The special case here, wake up! Hi, the special case, stand up, just sit up, it's more confusing, not standing up. Here, in this special case, what's the vector correspond to this minimal Condorcet? Out. How many people like ABC for this Condorcet scenario? The minimal one. I'm asking out. I don't know.
1?
Yeah! There's only one voter like ABC. Thank you. And John, how many people like ACB?
Nobody.
Right? Nobody. Yona, how many people like BAC?
Nobody.
Right. Edna, how many people prefer BCA?
1.
Right. CAB? 1. Thank you. So this is an example of a Condorcet vector, where you have this. Then you also have the opposite scenario. C beat B, beat A, beat C, analogously. So that's the 2 minimal, excuse me, okay, no touching.
Yeah, I know.
Okay. So that's the 2 minimal things. So for n equals 3, the number of Condorcet scenarios, let's call it C of n, or for n equals 2 times 1 plus 1. Let's stick to odd. So let C of n be the number of Condorcet scenarios with 3 candidates and 2n plus minus 1 voters. By the way, I was shocked that this famous paradox, the Condorcet paradox, that started with the French savant called Condorcet a long time ago, before the French Revolution, before it was still a monarchy. We're already worried, already anticipating maybe to be democracy. They were already voting. So many years, 25 plus, not tell me, 25 plus 200 plus 16, 241, a very odd paradox. So this sequence, the number of Condorcet scenarios that starts with 1, with odd, then later on we talk about, and with 2, sorry. With n equal 1 is 2, is not yet in the IIS. But very soon it will be. Andrew volunteered or got volunteered, my student, to enter it. What happened in my class today, we had a dry run, and we generated the sequence, and Andrew, being so smart, he was going ahead, what are you doing, and went to the IIS, and Googled the sequence, and no, OIS is the sequence, and it was not found. But it did find a polynomial of degree 5. So it happens that you have a polynomial of degree 5. So this was already known. A famous mathematical political scientist called Walter Gerlein, and in collaboration with a famous social social justice, social choice expert that probably Neil knows, Peter Fishbone. You know him probably, right?
Very well.
Yeah, okay. So in 1976, they found a closed form formula for this number for C of n. A standard polynomial of degree 5. But today, in less than an hour, we reproduced it in my class. And here is the answer, the theorem. The Fishbone-Gerline theorem from 1976. It's a beautiful formula. n-1, and that's what the OIS gave as a guess. It tells you it's not the OIS yet, but now OIS apparently has a feature that tells you the polynomial if it exists. So this is a beautiful, that's a probability, sorry, that's not the number. That's only the probability. So that's the probability for the Condorcet. To get the probability, you have to divide by the total number of such vectors. And that's an easy exercise in combinatorics. The number of ways of the number of such vectors is -6. Choose 2n minus 1. Let me explain why. The total number of vectors, regardless of the paradox or not. Why? Because the generating factor of this, you have decisions. You have 6 independent decisions. You decide about this. It's going to be 0, 1, 2, 3, 4, up to infinity. So, the generating function for each individual component is 1 over 1 minus x. And these are completely independent. So the generating function for all the tuples is this. And if you want to find those that add up to n, using the standard generating functionology, you look at the coefficient of x to the power n in this generating function. So this is 1 minus x to the power minus 6, the coefficient of x to the power n, thanks to good old Isaac Newton, who extended the Pascal thing to the fractional things, is this. And this is 5 plus n, choose 5. That's the total. So if you divide the correct answer, which I don't have here, you get the explicit answer for Pn. So that's the probability of the Condorcet paradox happening. So you let n go to infinity, and Ross, if you let n go to infinity, what's the limit of this? And n is very, very big.
It's 1/8.
Huh? 1/8?
That's what you have down, and I don't know why that would be. I'm getting a quarter. It should be a quarter, right?
No,
I see a 16.
16. 1/16. No, 2 times 2 times 2 times
1/16.
Oh.
And it is 1/16.
Now I'm more confused.
And this was proved by Fishbone. This was proved, quote unquote, by Fishbone and Gerline. But what's wrong with this probability? What's wrong with this in real life? Anybody? No, you already talked in class. What in class? What's wrong? Yes?
It means that it's likely that in a 3-horse race that we're screwed.
Said what?
That there's no good way to pick a winner in a 3-horse race if we all kind of pick.
Yeah, but what's wrong with the methodology of computing this probability? I divided the number of successful vectors to the total number of vectors, the number of Condorcet vectors to all vectors, and I got this.
That they're
But in a real election,
those aren't not uniform distribution.
right, it tacitly assumes that each of these vectors is equally likely. Like when you toss a coin, you either have a fair coin, you either have n heads and 0 tails, n minus 1 heads and 1 tail. But they're not equally likely. It's much more likely to have the same number of heads and tails than this. So we need a different methodology. But before that, let's first do this combinatorics problem. Using computer algebra, my computer, I have ready-made program to crank out the generating function for this. So this is an example of solving a linear Differential equation. There's a whole theory that started with Erhard and Richard Stanley also contributed of linear Differential equations. So let's look at this. What is the condition for the Condorcet paradox? Suppose A beats B. What does it mean? The number of voters who prefer A to B is strictly bigger than the number of voters that prefer B to A. So, Matthew, how many voters prefer A to B?
So in the example we did before, it's 2.
No, in this case.
Oh.
Yes. Alpha ABC, voters prefer ABC, and so on.
Okay, so it's alpha ABC, it's alpha ACB, and it's alpha CAB, and add those all up.
Yeah. Alpha CCB. This is the number of people prefer, the number of people prefer A to B. And this has to be bigger, so let's take away with the number of people who prefer B to A. So add. And how many people prefer B to A? How many people prefer B to A?
In there,
Yeah, so
I guess, 1,
so alpha BAC?
2.
No, not in the special case. In the general case. That's a vector. So
Okay,
BCA
2,
and CBA, right?
3, no, 2.
Yeah. So
BCA.
so yeah, it's a complement. If you know B to A to B, you turn B to A. So I'll do all I want. So alpha BAC, I'm confused. Mike, tell me.
BCA?
Yeah. BCA.
CBA.
CCA, sorry.
CB, okay, well,
C.
B,
BCA
BCA
and the other ones, right?
CA.
yeah.
plus
plus CBA.
CBA. Yeah, thank you. Okay, so I need more. So it was really a great application to a Maple package I had anyway for solving, for finding the main function of this. So, okay, so so A, CB.
You can't start with A because
Oh, no.
BAC,
Yeah, B,
BCA and CBA.
B, BAC,
BAC, BCA.
BA. That's D, C. Okay. Anyway, you can. Okay. But once again, you're gonna fit it.
Just do the first one minus all.
I need to make smaller. Alpha, okay. AB plus AB plus AB minus BA. C is coming up. Now you insert all the C. C, 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 C. Big or equal to 1?
The last one
Yeah,
is BCAC. No, that's good. That's good.
This one, and then BAC.
B,
BAC.
BAC. Yeah. Okay. This means A beat B, so make it do like this. Now B beat A, and analogously, and so A beat B, B beat C, sorry, and C beat A. You have three linear Diophantine inequalities, and in addition, you have the condition that all of them add up to n. How to find an informative generating function for all of them? So I'm looking for the infinity as the infinite set, sorry about saying infinity, but I mean it's infinity quote unquote, set of all vectors. And you introduce some bogus variable. Every inequality, so try to make like this. So let's use them, let's illustrate the algorithm in a more general context. We have a set of discrete variables, A1, AN. And you have a finite set of inequalities of the form sigma Ci AI plus or minus is a C0. I goes from 1 to n. And you want to count them, and you introduce a weight. The weight of a vector, A1, AN, is x1. You introduce continuous, so-called continuous variable, x for each discrete variable, x1, xn. And what you want is a grand generating function, sigma x1 over also to satisfy this family of inequalities. So here is a trick, and Maple can do it automatically. And this is a very general procedure. For each inequalities, you also introduce another variable, an auxiliary variable. Call it Z. So this is inequality 1, so let's call it J. There's a family of inequalities. J equals 1 to K. So Z1, and you put this into here. So then you have a huge, and all it does is sum, at the end of the day, some huge geometrical series. But then you extract all the positive coefficients. When you have a formal power series with negative powers 2, it's easy in the macro that only construct the positive part. So you have a huge and Maple yells, so all you need is a very naive command, convert to power fraction, which we learned in Calc 2 how to do partial fraction. But here we have several variables. So you keep iterating it, and lo and behold, you get a generating function for the inequalities. And if you did it for Condorcet in 20 seconds, I got a brand new result as far as I know, not as a plain generating function, but the global one that keeps track of all the scenarios. So it encapsulates all the possible Condorcet scenarios. And as far as I know, it's new, also, I may be wrong. I don't see it ever published. So here is a beautiful generating function that keeps track. So t is the length. So this is a generating function. I'll explain in a second. So this is brand new as far as I know. If you have seen before, please let me know. I'll be upset, but I'll be thankful. This is the grand generating function. And the denominator is 1 minus t squared. And what's beautiful about this, it gives you insight. These people, stupid people, say,